to our series. It revolves around the intersection of AI and physics simulation, specifically how to integrate PDEs with data-driven approaches. And Peter is currently a postdoctorate fellow at MIT CSAIL, working with Wojciech Matusik, who we've collaborated with in the past as well. And next year, he'll be starting at UBC. So with that, I'll hand it over to you, Peter. Please take it away.
Awesome. You're all right. Let me share my screen. 1 second. Let's see. Share screen. The other one. And let's go here. The first one. Right here. All right. Yes, I'm very happy to be here. Like Nigel said, currently I'm a postdoc at MIT, but I'm starting as an assistant professor at UBC, where lots of our efforts is, using AI to solve these scientific as well as engineering challenges, which is quite different from, let's say, like a computer vision task, right, where there are lots of data. Okay, so physics simulations are everywhere, right? So here is an example of us simulating bread fracture. I guess this is more a computer graphics sort of setup and VR, AR setup. It's also crucial for, scientific problems, right? Like here with my mechanical engineering colleagues, we're studying the flow of these granular media. You guys hearing me okay? All right. So this is a granular media, right? In this case, we want to study the flow profiles. And instead of, going to the beach, set up the, doing the experiment, you can do this in a completely, simulation setup. And it's also useful for engineering design problems. And here with my robotics colleagues, we're trying to design these underwater robot that is, have better lift and drag ratios. And thanks to having a nice simulation, this entire process is automated, and we can design it and then fabricate it. It's also useful for VRAS setup. We with Meta Reality Lab, we have lots of collaboration where you can have these users, having this shared physical environment where they can, play, game of Jenga like this, but also doing, more serious like engineering design problems. So how are these simulations done? They're traditionally done through these classical numerical PDE solvers. These solvers generally, it's a very complicated thing, right? Everybody has its own solver. There are lots of steps, but generally you can break it down to two parts. One is, the equation, right? This is right on the equation, the physics. There's no computer science here per se. So this is just write down your equation, depends on your field. You're simulating soft stuff, fluids, or or EM stuff, right? So different equations, and then you solve it. And this is where sort of computational scientists come in. You have to describe this sort of domain, spatially as well as temporally, right? And this involves linear solver optimization and lots of different steps. So like I said, this thing, it has been really it's a foundation for modern science and engineering, right? So different fields, even just myself, I've done granular mechanics, fluid science, composite material, even these biology problems, designing robots, as well as the RVR problems. So these simulations are really the pillar of science and engineering alongside theory and actual physical experiments. So this thing has been around for so long, but what's the problem? Very often you run into accuracy issues, right? These accuracy issue can, maybe your equation is incorrect or the solver is incorrect, and speed, right? So these things often take days and weeks to run. Then it's not very useful if something takes weeks to run if you want to design something. So speed is another problem. And another problem I would argue is obviously speed versus accuracy. This is very traditional pillars, right? But I will argue that in practice, another thing is what I call accessibility, which means running this simulation often involves heavy parameter tuning. Grad students, engineers try to tune these parameters, and it requires very deep domain knowledge in order for someone to get there to actually run these simulations. So they're not easy to run. So there's this accessibility challenges. So I bring this problem to my machine learning colleagues, right? I used to be very anti-deep learning, anti-machine learning. I was like, what's going on there, right? But because when I bring these things up to them, they were like, yeah, we can solve the problem for you. But I was very, very skeptical. But listening to them, I started to feel like, okay, maybe it makes some sense, right? Maybe accuracy, right? Accuracy not in the sense of that, solving the PDE exactly, but rather accuracy in the sense that if you want to fit the data really well, like let's say you have some data, you some physical experiment, you want to fit the data, these neural networks can fit your data quite well. And also these neural networks are very fast to evaluate, which makes them very efficient. It also makes the modeling quite simple in the sense that you just tell me what's your input, what's your output, and then I'll just train the model for you. So make things a lot easier to build a model, as well as at inference time, you just press click and just inference. No simulation blow up, no numerical issues, anything like that. Okay, so I was skeptical. But this looks promising. But let's take a look at a particular case of using AI to really help simulation. So in this case, let's say we're modeling this fluid dynamics problem. You have these soft bodies falling into a pile of water, and then traditionally you have to simulate this in time stepping this, right? Break down into different time step, and then each time step, let's say you use a graph neural network, right? This is a signature paper by my colleague Tobias at DeepMind, right? So this is a great paper. We have lots of follow-up paper on this as well. But we did find that this paper has some limitations. So for example, as you can see that when you train on data, like this cube data on the left, it doesn't quite generalize to a different geometry, right? Let's say we want to change the geometry, not a cube, but something else, right? Because in design problems, often we want to vary, the shape, the mesh, but then the simulation just failed. So in fact, we realized after training on some data, it fails to generalize in lots of different cases, like boundary condition, initial condition, we're simulating longer time, we're doing more complex physics, multi-physics and phase change. So in other words, what we're observing is that very often with the end-to-end neural network approach, we run into these generalizability issues. Why is that the case? Probably not surprising because of lack of physical laws. So in this previous case, right, we know that these water should generally follow, the Navier-Stokes equations. Generally speaking, we believe that. I was at University of Waterloo the other day, and they were like, no, maybe we think there are other terms. But generally, we think, F equals ma is true in this context. But these equations were never really incorporated either during the training or at inference time. So that's why these methods don't generalize very well. So we're facing that, these end-to-end neural network has lots of promises, but it has challenges in generalizability. We also have these classical methods that has good generalizability, right? You can pretty much model anything you want with this approach, but it faces other challenges. So obviously there's a huge spectrum of methods in between, and that's where my research explores this in-between area, with the goal of making things accessible, accurate, and fast, while still keeping, this generalizability. I call my research, neural PDE, right? The neural parts hopefully give us the green parts, and the PDE parts will still make sure we have generalizability. So I guess the slogan of my research will be keep the PDEs, do not throw them away. So in particular, I found this formula to be quite successful in my research, which is using neural network to sort of represent X. So this X can be something about the classical, numerical PDE solver components. Let's say spatial representation, linear solver, parameters, material models, or time integration. But we only insert these neural network, or these data-driven parts, very carefully and replace some parts while keeping the rest of the classical PDE solver, so that we can have things that satisfy these accessibility, accuracy, speed improvement, but still keeping the generalizability part. So today I'll go through a couple of different papers, in with application to machine learning, computer graphics, scientific computing, and robotics. And for each of them is essentially replacing this X with a particular problem of the classical numerical solvers. So let's first talk about accessibility. In this case, we want to use this neural network to enhance parameter identification, figure out the parameters of your numerical PDE solvers. And we only use that for this purpose. We'll keep the rest of the PDE solver. So these input parameters, right? Let's say you want to set up simulation like this. There's geometry, right? There's material parameters, right? Like Young's modulus, Bach modulus, right? And as well as the mesh here. So these are input parameters to your simulators. So traditionally, try to figure out these parameters are tricky. You go to the experiment, you go to the lab, you set it up, but not often these parameters can be directly applied to your particular setup because there are other numerical parameters that cause things to differ. So traditionally, it requires lots of manual processes to tune these things. So in this line of research, we're trying to ask, how can we actually identify these parameters? Let's say directly from videos. That will make life a lot easier, right? Let's say we observe some physical phenomenon that we're interested in, whether in the real world, like you have this water bottle shaking, or in the lab, you have some microscope looking at something, or whatever that case is, you have some visual data, right? And these data come in like 2D and temporal sequence. What if we can recover these parameters directly from these input videos? So I will not go into too many details here, but here is the pipeline, right? So essentially, these parameters serve as the input to your solver, right? Your PDE solver, your numerical solver. After that, this PDE numerical solver can be put into computer graphics techniques like rendering techniques to render these things into these 2D image sequences. And then once you have these synthesized videos and compare them with the real world videos, and construct a loss function, right? The goal is to optimize these parameters so that these videos, synthesized videos and real world videos match. So we do that through, again, inverse optimization. The reason we can do this is because this entire pipeline is differentiable, both the rendering part and the differentiable physics part. So this differentiable physics part, essentially, there's really no neural network here, right? This is just your traditional numerical PDE solvers. You write down the equation, you write down the weak form, you discretize it properly. This is the traditional solver, but we also leverage differentiable programming to do this backward pass. In particular, in this case, we're leveraging NVIDIA's work to do this. So we had a SIGGRAPH course on differentiable spatial computing for Python using Warp, right? So compared to we've also tried different things, Tai Chi, PyTorch, JAX. Warp is the nicest in terms of performance, as well as, how easy it is to actually solve these problems while giving you like a low level control. So again, there's no neural network involved here. This is just implementing everything in a differentiable programming context. And we did some experiment, we showed that we're able to recover various material properties, Young's modulus, as well as, friction parameters. And it generalized to, because in this case, there's really no neural network or data-driven part per se here, right? It's just inversely identify your parameters so that it works for, different things, right? Newtonian fluids, non-Newtonian fluids, elasticity, plasticity. And we, more recently, we extend this to sort of robotics setup, right? Let's say you have a robot, right? You're manipulating some objects, right? Like, let's say you have a robot head manipulating these. How can I actually figure out, let's say the fluids, inside or the material properties of this thing? So very similar setup, but to the previous setup, right? So you do experiment like this, and then we're able to figure out, the material properties of the mass of this sphere here, based on observing the motion of the ball. And here, figuring out the material properties of the object that you're sort of squeezing, right? Through differentiable physics here. Great. So we see that, these differentiable framework allows us to identify these parameters this makes life, a lot easier, right? So I want to comment now, some potential opportunity, right, with Autodesk, right? So differentiable physics, right? So we're talking about parameter identification. That's obviously a very important use case, right? Let's say like BMW designed some material, right? And they want to do some material testing, right? Some new design, and then you can you observe certain things, and then you can inversely create a digital twin of that model, right? So that's very useful. Parameter identification, identifying these digital twins. But in addition, inverse design is another thing, right? That's very useful when you have a differentiable physics engine, right? So in this case, we're designing these underwater gliders, in the swimming pool. So we want to design these gliders so that they have very optimal lift and drag ratio. And by having a differentiable framework really allows us to iterate the shape of these underwater glider. Thanks to the differentiable physics, right? So we can there's a certain loss function and want to optimize with respect to that to change our shapes. And just recently, we're discussing, let's say, this is the solver we're using is a static sort of solver. We're talking about, the XLB solver that Autodesk developed. I think this is quite exciting. So another thing I think that could be interesting that we can potentially explore is using these LLM agents, right? So in this setup we talk about, in the previous setup there's everything is done, still requires lots of domain knowledge, right? Like I need to pick, let's say again, let's go back to the BMW crash a car, right? Let's say we want to figure out the digital twin of that model. It still requires lots of expert to go in. Let's pick them. What's the best solver for this context, right? This is probably their fracture, well, not fracture, but there's plasticity involved, right? So all those things, we require an expert to do it, right? But instead, I think there are lots of room, right? Like you guys are exploring using this LM agent to do lots of tasks that is traditional, require lots of human intervention, right? So let's say we see this observation of some physical phenomenon, then we can leverage, these LLM, VLMs to figure out, okay, this is, this thing is there's solid fluid coupling there, right? This is probably simulated best by through some finite element, as well as some, particle-based, fluid solver, right? And then you can combine that with the differentiable physics we talked about earlier to actually inverse identify the parameters, right? So this LLM agent is very useful, but also potentially, we can leverage program synthesis techniques, right, to actually generate these programs so that we can actually fund material model or particular setup that is particular useful for the scenario that we're observing. Questions, comments? This first part?
Well, I had a question, Peter. When you
Yes.
were talking about the differentiable renderer, were you also using Warp for that too, or another tool?
Yeah. So the differentiable rendering part is done through PyTorch, because it's just easily available. And I think that's the beautiful part of Warp is that it really is very, very compatible with other things, right? So
Yeah.
let's say you want to use Tai Chi, then or even JEX, you have to copy these things and then introduce like computation overhead.
All
Yeah.
right. Okay, cool. Thanks. Like Torch Vision, I assume.
Yeah. Um, cool. So all right, so let's move on to the next part. So we tried this technique, right, where we're trying to inversely get these digital twins from videos, right? We tried on some real world data. Then we run into some issues. I realized it's actually kind of hard to fit these to find the correct material models directly using these material models. So this leads to the second part of my talk, which I want to talk about having these neural network enhanced material models. So why don't we have a very accurate digital twins here? So in this particular case, is that if we look at these equations, all these equations, they have some sort of material models term. So for example, this is the same equation, but different material models. Hyperelastic model, this is Drucker-Parker model, von Mises yield condition, and weakly compressible fluids. Even though it's the same equation, but depends on the material model, you can have vastly different results, right? So this is also we were talking about earlier about, let's say maybe we can use LLM to actually pick the right material models for us. But the problem is that these traditional models, they are part of your numerical solver, right? So in this time stepping scheme, right? So this differential physics part. This material model, some of them are just not expressive enough, right? So even though, we can have, LLM to help us pick the one that is best for the scenario, it's still possible that it doesn't fit the data very well. So in this line of work, we want to address these accuracy issues by using these neural network-based material models. So why learning material models? Because they have been empirical models anyways, right? Like the simplest material model is probably, Hooke's law, right? This force is linearly related to your displacement, but why not nonlinearly? What if you stretch it too long, right? So this is a empirical model anyway. So it's a really good place to learn this thing. But obviously, when we learn it, we want to be careful, right? There are still certain physics we want to make sure it happens, such as rotation equivariance, and undeformed state equilibrium. So we bake in this into our network design so that we enforce these physical priors, so that we still guarantee thermodynamic consistency, stress symmetry, objectivity, and material symmetry. But it is still a neural network, which means it's very, very expressive. So after fitting these neural material models, we can see that it matches the real world video better than these classical material models. And what's really nice is that it generalizes. So in this case, we replace this cube that we use with a star-shaped thing, and it still works because this is probably not surprising because we're still solving these equations. We're just learning a material model that is different. So in the machine learning language, this means zero-shot generalization. So it works well, right? This is really a hybrid neural network PDE approach, right? Because the neural network is only used to represent your material model, but your traditional solver, your spatial digitization, your time integration are still done in the traditional way. So compare this with a pure data-driven approach, which replaces everything with neural network. What's the benefit? Well, the benefit is that if you throw away the PDEs, then you're essentially throwing away conservation of mass, moment, and energy, which caused the problem that we saw earlier, right? This type of, if you throw away too many things, this thing doesn't generalize, generalize to different geometry, but we still keep the PDE. So our hybrid neural network PDE approach generalizes to different geometry, generalizes to different initial velocities, boundary conditions, as well as simulating longer time. And again, if we train different types of material, then we can couple them easily, through traditional methods, as well as changing phase between them. And even generalizing to like degrees of freedom that is significantly larger than the training data. In this case, go from 1,000 to 1,000,000, as well as supporting context, right? So in fact, we see that on these generalization tasks, this sort of hybrid neural network and PD approach are over 100 times more accurate than these pure data-driven approaches that do not keep the PDEs. So why keeping the PDEs? The PDEs allows us to use less data to train. Like we talk about, this really, if you even just training on one trajectory, there's actually lots of data. I mean, there is enough data, not lots of data. Even just one trajectory, think about it. If you have like spatially lots of degree of freedom you are observing, and each of them, is using the same material models. So it's still, let's say you have, 1,000 degree of freedom and, for like 100 times that, that's still quite a lot of data. But it's not like lots of trajectories. We only need one trajectory to train, so it's less data. And because we're not trying to model everything, we're not trying to ask the network to implicitly learn mass conservation, momentum conservation. We don't need a giant network. We can use smaller network and therefore faster to train. Again, more recently, we extend this to sort of robotics context, right? So in this case, we have this very simple robotic arm here. We thought, okay, this is a well-solved problem, right? Modeling these robotic arm. Yes, in theory they are, but let's say you know the current, right? Because these models are really, let's say, we only know the input current, right? How much current you're applying to these joint motor and predict its motion, right? It sounds like a very simple problem that has been solved. But in fact, actually, if we use these classical models, right? In this case, you're solving these Newton's equations, right? We actually observe quite a bit like sim-to-real gap here, right? So you can see that the reality and the simulation doesn't quite match well, because basically the key is how can you actually convert this current to a torque model? It's not that clear. It's not that a simple model, and there are different backlashes, different things going on in the motor, so it doesn't really perform exactly like what you predict. And then we try this with these neural consistent model, right? In this context, the material model is sort of the current to the torque model, right? We can see that we can actually match these things much better. So this is nice. So using neural network to particularly replace parts of your equation, right? And we're still keeping the rest of the equation, so it allows you to generalize, but it gives you better accuracy. Again, I think there are different opportunities, to explore collaboration here. For example, in this insertion context, right? Like you have this robot, you try to insert into these holes, right? So this is a very, very delicate task, right? So having a better simulation model, right? If we can close this sim-to-real gap, that would be really, really nice. All right. Questions, comments on this second part?
Can you also point out the paper on this part or the series of papers?
Oh, the papers, yes. I I don't. This is. I think this is ICML 2023. Yeah. So I think the paper's name is called neural constitutive laws. Yeah. Learning generalizable PDE dynamics through observation. All
Thank you.
right.
Peter,
So
on your plots with I think it was the motor, learning the motor response.
right.
Could you go to those?
Yeah.
Um, okay, so the blue here is the measured response, and then the green is your predicted.
Yes. With if we augment parts of the, this is a very simple thing, right?
Yeah.
Rigid body dynamics, right? There's no surprise. So that physics is very clear. But what is unclear is that depends on how much current you apply, what torque is it actually applied in
Right.
your motor. It depends on the state, You thought if you apply constant current, then this thing will move, apply constant torque, but it's actually not the case.
Mm-hmm. So it seems like there's almost these little steps that are happening in the actual the measured responses. Is there and like the model is very smooth. Do you think there's a way to incorporate that kind of stepping phenomena as well in the model?
Got it. Right. So data is very helpful, right? But what if there are lots of noise, right? So I think there's a sort of a
Yeah.
trade-off here, like how much do we want to fit the noise? Yeah.
Hmm.
But I can imagine, right, for certain times, it's not a smooth motion, right? Then you should be able to predict.
Right.
Yeah. And add certain, stochastic terms. I think that's great feedback. Yeah. I think.
Oh, hello. Yeah, thank you. I really like this neural constitutive model because I think we're doing some work as well that I think it's similar to this. So yeah, quite interested to follow more. So just a question. I guess I'm just curious. I think we could technically set up a like a material model learning, by just we can choose like some sort of like hyperelastic, potential energy function with some sort of tunable parameters and just do the usual like inverse problem. So I'm just kind of curious, could you comment on the specific like benefits from introducing a neural network in this case?
Yeah. So I think, we can set up these traditional material models, and they work generally pretty well. But in our case, right, we did observe that so this model here on the left is doing exactly what you said, right? Which is we picked the essentially the hyperelastic model and the von Mises yield condition. So that's what we pick, but it has a problem fitting the data that we observe, right? So in this case, we in this particular case, the reason is because these traditional material models are not expressive enough for this particular task. Yeah. So I think this sort of neural network based model is very useful for complex materials, let's say biological materials, right? If you're doing like simple things like steel, right, it's probably not so interesting, right? But if it's complicated materials like biological materials, I have some collaborators who work on these biological materials. Their hyperelastic model has like 100 terms. They're not neural network, but like, just polynomials, 100 parameter. So it is a very heuristic approach anyways. Yeah. And that's one benefit. And the other one is that now you have a unified model for everything, instead of designing these things, maybe for certain problems, it matters. So instead of designing these things one by one, right? Now, we can have these neural network models, one single model that's able to represent all these different behaviors with different parameters, but we don't have to, design them, one by one, right? Yeah.
So you mean similar neural architecture that respects the material symmetry and all that stuff, but then, but tune the parameters specifically for the different materials.
Right. So in this case, it's the same. It's different parameters. You have to use different parameters for different material, but it's complete the same architecture. Simple MLPs actually. Just map your strain to your stress. Well, obviously with certain, we'll also make sure we enforce certain physical priors. Yeah.
Cool, thank you.
Maybe one last question for this section I have. So you showed a video of the real world versus the simulated results. How do you know that the error is due to the material model, not the simulator? So how do you make sure that you isolate the material model error versus the solver error?
Yeah, I think that's a great comment, right? So because for example, like this depends on the mesh you use, right? You can have different results, right? Different time step size will give you different results, right? So I think the rule of thumb is that you do your diligence, right? Make sure you're using small enough time step and use the mesh fine enough. But after doing all of these, you still observe this sort of gap. And I think that's the case where, okay, my material model is probably, could use some help.
Okay, fair enough. Thank you.
All right. So let's move on to the next part, right? Speed, making things faster. This is everybody's favorite topic. So simulations are slow, making them not very useful. There are different reasons. One particular is that we have to introduce this spatial digitalization. So So this spatial digitization, we can introduce them. This spatial digitization depends on they can be grid, be mesh, the point cloud, but really depends on the basis function that you use. But regardless of the basis function you use, you have a very large number of degree of freedom, large number of samples. So they are slow to compute. So one of the reasons that these things are slow to compute. So people have been using reduced order model to actually speed up these simulations by addressing that large number of degrees of freedom. So this is really the OG approach towards machine learning for physics simulation. So generally, reduced order models start with some, high dimensional data, right? This data are very high resolution, and generated by simulators or directly from experiments, right? So they're high resolution, and then these reduced order model attempt to learn using whatever techniques, curve fitting techniques, to learn a lower dimensional space, and then map this lower dimensional space back to this original high resolution data, because you still want high resolution results. But it is fast because you're essentially updating, you're solving your physics instead of in these, solving every mesh vertex directly, every grid nodes, right? You're solving in this low dimensional latent space. So this has been around for a very long time. Traditionally people use, PCA, POD, type of techniques, so that this is a linear mapping, go from your latent space to your discretized values, right? So on the left, your latent space, on the right is, different, let's say, like your vector field, I don't know, maybe it's a velocity field, right? Each of these particles carry a velocity value. More recently, people start to use neural network to do this, right? Like this is a nonlinear approach, which has lots of benefits, in particular for capturing advection dominant problems. But regardless of you're using linear methods, we're using these autoencoder approaches, you're still sort of stuck in this traditional architecture, which doesn't quite allow you to have information outside of these fixed degrees of freedom. It also doesn't really, if you train a model, right, it has to be stuck. You have to pick a resolution. After training, you can't really change your resolution, where your training data cannot come in with different resolution. And obviously, adaptive mesh refinement data is not impossible to be captured in these scenarios, because essentially you're stuck with one mesh, one grid, one set of points. And if you can't even change the mesh resolution, don't worry about changing the geometry, right? Like even, let's say, this shape thing, I don't know what kind of shape is this, but let's say I want to make it a bigger shape, or I want to, have other features, that's also impossible. Or punching some holes, right? That's also just not possible. So really, all these problems are one problem, is that this sort of low dimensional manifold is built for the discretization of the continuous system instead of the original continuous system itself. So this is really the key insight I would like to convey in this line of work, is that lots of these reduced order models are built for the discretization of the continuous system instead of the original continuous system itself. So we really need a new approach that is not bounded by a particular discretization and has the capability of generalizing to different geometries. So we propose to solve this by tweaking this architecture, this low dimensional manifold, tweaking its input and output. So in this case, we still have this low dimensional latent space here, but instead, our low dimensional manifold here, this function here, G, takes an additional input of X, where X is whatever point in your spatial domain, and the output is no longer discretized vector field, but rather the continuous vector field evaluated at that particular location. So this allows us to query arbitrary points in your spatial domain, and therefore, your data can come in with different resolution, and after training, you can evaluate at different resolutions. And then, data can also come in with adaptive match refinement data is fine as well. And even let's say we want to change this domain omega, that is also possible, and topology change. So this simple architecture switch allows us to address all the problems that we saw earlier. And now this training data can be any digitalization of the regional continuous system, right? Let's say, you want to solve the Navier-Stokes equation, right? But you can really solve it in different ways. You can find an element, find a volume, or find a difference, or some sort of particle-based method. But it's the same equation, right? You're solving the Navier-Stokes equation. So this one architecture can fit any sort of digitalization of that regional continuous system. So we built it using a quite simple architecture, neural field or MLP architecture, really. That being said, want to emphasize that here. Here is we don't want you guys to go away with, okay, this guy applied neural field to reduce order modeling, right? But yes, I did apply neural field to reduce order modeling to solve physics and PDE. That is true. But really the key insight is the digitalization-free representation. It's actually come out with a low-dimensional manifold that allows you to directly approximate the continuous vector field itself. Maybe it doesn't have to be a neural network. In fact, recently we showed that we actually don't need a neural network here. Like even a linear method here works quite well. All right, so we have this terrific digitalization-free representation. We're trained on some data, right? You train on, again, your velocity field, but let's say this is, I don't know, displacement field. But in addition to ensure your model captures displacement field, you can also ensure it captures, let's say, the deformation gradient, like the gradient of your, whether it's spatial gradient or temporal gradients of your vector field, if those information is available. So you train on some data, you observe this, you obtain, so after training, so how can we run you dynamics on it? So I will not go into the details. If we have time, we can talk about it in the end, which I'll just, on a high level, there involves 3 steps. First, you want to go from this latent space back to your physical space. And then you do a time integration in your physical space, and then you this is your traditional PDE solver, and then you project it back. So through, nonlinear least squares. So here, as you can see, neural network is really involved in the inference and the projection part. So they're really serving as a spatial representation. We do not learn the temporal dynamics per se. Obviously, you can learn these dynamics, but in this particular case, we're not learning these dynamics, which allows us to generalize to different things because we still keep the PDEs here. And since this dimension of this Q is very small, let's say 10, 20. So because this is small, so we can actually do all these 3 steps, just instead of very, fine match, let's say 3 million degrees of freedom, we can just, pick 50, sample degrees of freedom in order to drive this sort of updates. So that's where the computational save comes from. Okay, so let's see some results. So here, we show that we can train on different digitalization. This is, fractured, not fractured, right? So again, traditional methods cannot even train, traditional reduced order model cannot even train on this kind of data. So even just training on this data, this is a new capability. And what is even cooler is that we can actually, after training on just the data on the left, we can actually do gradually topology changes, right? So this is the reason we can do this is because we keep the PDEs so that we're still solving PDE at the same step. And the neural network is only asked to be able to capture this sort of spatial distribution. Yes, so previous digitalization dependent methods, PCA autoencoders, cannot handle data with changing geometries. So this is a example we call it swapping horses midstream. So what do we mean by that? Essentially, we train this model on these alls, right? These all-shaped mesh. But after training, we can actually swap in different meshes, swap in different geometries. And this is, real-time capture, a lot faster than the non-reduced model. And we can swap geometry at any time. The reason we can do this is because, the solver, you're updating these latent space. But as you update this latent space, at any moment, you can swap in whatever geometry that you want. So again, this is, in machine learning, we call it zero-shot generalization. It's only trained on one mesh, but actually generalizes to different meshes. And as such, there are lots of exciting opportunities, right? Let's say robot manipulation. Let's say we want to manipulate these different geometries, right? Different bags, for example, right? So we've also recently, generalized this even further, instead of just training on one geometry, generalized to, let's say 3 or 4 other geometries. We actually pre-train this thing on the entire shape net, where there are lots of shapes. And after training, we're able to, again, one single model that is able to simulate all these different geometries here, right? You see different cubes, different chairs, different cars. Again, one single model that's able to handle all these different things. So this is, and because we can now have a consistent across different, one single model that's able to capture all kinds of geometries, this means now we can do shape optimization, right? We can actually figure out the shape, right? That's that, let's say, that's the best locomotion, right? So we can actually optimize and obtain these different shapes. And here, essentially, we can see that, this is, we can, let's say you have these sliders, right? Allow you to explore different shapes, like of a bridge, right? And then then we can actually compute its stress. We can do static stress analysis. Actually, not static stress analysis. We can actually simulate these things. I think we're still solving the temporal equation, the elastodynamics equation, in real time. So it's probably not very clear, but you can see these bridge, they're actually bouncing a little bit. So where as you drag the sliders, you have a different shape, and then we're still simulating them in real time. So this is, so basically we took the data, these bridge data, from, on-shaped CAD models, and no meshing is needed. I think we didn't really emphasize this part because, again, continuous vector field directly represented through these neural fields. So we don't really need meshing in this case, which means we can work with any representation, directly work with CAD, with, sign distance field. So with no meshing overheads here. So this is real time, like I said, as you move these bars, they're actually simulating in real time. Yeah, so this is still ongoing work. There are more details here. In this case, we're learning the eigenfunction of different elastic energy and Laplacian energy. So I don't have the time to go into details here. This is work mainly, led by, my University of Toronto collaborators. So if you guys are interested in details of this work, I'm sure they're happy to talk more about that. So again, we're not bound to a particular digitization. It allows us to change geometry and also capturing things like fracture with a reduced order model. Like complex fracture like this can be captured using a latent space dimension of only 6. It's featuring the NVIDIA GTC this year. Speed up, we talk about it. Also, zero-shot super resolution, training on low-resolution data, evaluate high resolution. This is impossible with previous approaches. It also works with fluids. So in this case, we're able to capture, from static flows bifurcation to vortex shedding. And this simulation can go on for a very, very long time. Even, again, the point of this example is to demonstrate that we do use neural network But the neural network is only used to build us a sort of a function space. But the solver is still done through the traditional methods. So therefore, we can drive these simulations for a very, very long time. So we all want a foundation model of physical data. What does that mean? I think, there are different ways to interpret it, but to me, I think one important thing is, can we even train with different data, right? If you always need to do some meshing, convert mesh to point clouds and train, that is not very nice, right? So in this case, we propose this framework really allows us to train on all kinds of data that can be, that you can get, right? As well as, so really our approach, our sort of North Star goal is this kitchen sink ML model for different physical data that, generalize the different geometries, initial boundary conditions, and different PDEs. So this is the third part of my talk on this neural network enhanced digitalization for representation to really speed up these solvers. And I think there are a lot of very concrete collaboration opportunities with Autodesk, right? So you guys are doing amazing work in these 3D shape generations, and in particular, CAD generations that enforce these CAD models, right? So essentially these models sort of have a latent space representation, right? So that's essentially sort of correspond to like this example. We have this different shape representation, right? And then how can we actually really fast simulate these generated shapes? So essentially, the trick is to how can we map these shapes to these low-dimensional representation and therefore simulate them really, really fast. And once that you can simulate them really fast, again, because we're not bounded to a particular representation, we can directly work with CAD models or any kind of shape that is being generated. And because this is a single model that is able to represent everything, it really allows us to do design problems to actually find the optimal shape for a particular target. And I think that's very, very exciting. All right. So I guess we have 3 minutes left. Any question for this last part?
Yeah. Oh, sorry. Go ahead, Jeremy.
No, I can go ahead.
Okay. Yeah, thank you for the talk. It was incredible work. I'm actually very curious about the continuous ROM work that you did. You mentioned that you only needed a subsample of the points within the object to be able to integrate the PDE. I wonder if you might be able to go a bit deeper into that and how that works.
Right. So essentially, we're trying to figure out, you have some points, spatial points, right? And you update them temporally. And then essentially to update your latent space, you're solving a least square problems. Nonlinear or depends. A least square could be nonlinear, linear, depends on representation. So to solve this problem, because the dimension of this queue is very, very small, so you can actually, so this is an over-parameterized problem. So it's an over-determined system. So therefore, not over-parameterized, sorry, over-determined system. So therefore, instead of using all the degree of freedom, let's say 3 million, you can choose a subset of these points. So obviously, how to choose them, how to pick them, that's science, right? Depends on your problem. Let's say you have shear localization type of problems, and then you're still sampling them like randomly here, then probably won't work, right? You want to sample very densely where there are lots of features, right? But that's in theory, so this is a reason why you can use the fewer points, but obviously it depends on your problem. You want to sample these things more carefully.
Yeah, I suppose my question was the time integration between Fn to Fn plus 1. Does that happen on a subset of points, or does that happen on kind of a mesh that you create as well?
Yeah, that happens on a subset of points. So, maybe imagine it's an explicit methods. So let's make it easy. We do this for explicit and implicit. But if you think about explicit methods, right, then you can just update them on their own, right? Like you just compute the force and update them all. So that's it. So that's how it works. And implicit means basically if it's an implicit method, then you need to solve all the points together and you do a solver kind of step. Yeah.
I see. All right. Yeah. Thank you.
Is it my turn? So Peter, thanks. So in the case of so I've read your C-round paper. I'm quite familiar with it. And so the function that's output of the INR, let's say for the case of Navier-Stokes, if you want to reconstruct the PDE, and you only have velocity as the output and not pressure, how would you go about that? In the
Yes. So I think for the Navier-Stokes, right, you have two, I mean, if it's incompressible Euler, you have to solve both the pressure parts and the velocity field. So essentially you want to build a latent space for both. They can share a latent space, they can have their separate latent space, but essentially you want to reduce the pressure field as well.
Yeah, the issue is that they're not kind of independent. Like there's the Poisson equation that relates them. So we're kind of ignoring that by doing this, I suppose.
No, I think we built a shared latent space. Sorry, where's that slide? Sorry, too many slides. So this PDE time integration part, right? So if you're solving, maybe we just show one simple example. Let's say you're solving heat equation, right? So this is just one term, right? One equation here, right? So in this case, you're essentially, this sort of also answering Baccarat's problem, right? So you update for every spatial samples you have, right? You can obtain, if you do a explicit update, right? You can basically solve for whatever this u dot n plus 1 is, and then you do this sort of updates. So in the case of Navier-Stokes, the way we did it, obviously there are different ways to implement it. The way we did it was still follow the Trorin pressure projection style, meaning that we sort of we do the extraction first, and then we do the projection. So we still do both steps in our solver.
All right, thank you. And you're only using the inversion, like the least square for doing going back from the actual space to the latent space, and sorry, latent space to the actual space, or vice versa. And you're not using your encoder, right?
Correct, but there could be, I think there are different flavors if you want. Yeah, you could, let's say, use your encoder to do that.
Because the encoder would not be mesh free.
The encoder is our latest work. We use a point net for that, right? So point net, essentially, you can still basically take in different. It is mesh free, I guess, in that sense. You just need to sample the space. But you're right. In my long time ago GitHub implementation, I think we use a very naive encoder that is discretization dependent, and which is not nice. Yeah.
Okay, thank you. And this was an excellent presentation. Thank you so much.
Thank you.
Hello, yep, it's me again. Yeah, so very interesting again. So my question has to do with the zero shot generalization. I think with the pulling, like swapping the horse kind of midway. So I'm just curious. So I guess intuitively, I would think that depending on like, kind of the small scale geometry features that you have, like I probably would like respond very differently. I'm just kind of thinking. So I'm just kind of curious, like, like how do you ensure the accuracy, like the kind of the problem dependent aspect of your approach? Like I'm guessing, like I guess that would look like the mapping from the actual like full state to the latent space. So that I can see being problem dependent. And I think the latent space potentially could be as well. So how do you actually tackle that?
Yeah, I think there is a trade-offs between how well these things generalize.
Mm-hmm.
They, for things that accuracy is not important, like VR, in the meta setup, it's fine, right? But like you said, I don't expect these thin features to be captured very accurately, correct?
Mm-hmm.
But that's also asking us a lot, right? You train on one mesh, generalize arbitrary mesh, right? That's asking a lot, right? So I think our so but this framework does allow you to train on more shapes, right? Like the shapes that are interested in, right? So then I think it boils down to, if we want to increase accuracy, right? We probably want to increase the training data set. Yeah.
Yeah, that's really cool. I mean, it makes sense. I think maybe the key is to kind of identify if there's sort of any commonality between the problems, that I guess the different variations of the problem that we want to solve, and focus on learning the generalizable features, whatever that is, between the
Right.
problems. Yeah.
Yeah.
Okay, cool. Thank you.
All right. Last question.
Thank you very much for the great presentation. So I have a question. So you specify 3 areas for justification of using neural net for generalizability, accuracy, and speed.
Right.
So most specifically on the last part of the presentation about the serum, it seems that it has addressed the speed aspect of that
Right.
uh, advantage of those 3 advantages. How about the accuracy? Have you done any quantitative analysis between the ground truth and the results you get out of the neural network?
Yeah. I think in the Cron paper, the CRON paper, we have these, like any reduced order modeling paper, I guess, we study. So there is always a trade-off between speed and accuracy, right? So it depends on the number of points you sample, right? Like we're talking about, these, if you sample very, very few points, right, it's not going to be accurate, right? So, but if you sample more points, right, it does converge, right? So that's one part of the trade-off between accuracy. And the other one is, what, Jamie said, like if your mesh is significantly different from your training data, then it will suffer from accuracy issues as well. Yeah. So at the end of the day, I feel like it's all about trade-offs that depends on your problem. Yeah.
Okay, and so one last part of the my question, you claim that you can also address the topology variation with this
Right.
approach. So
Right.
in the example you showed, the topology was quite similar to, at least what it was my understanding.
Yes.
It
Yes.
was similar to what you had in the training set.
Right.
Uh,
Right.
how? Yeah, not this one, the one that you were tearing
Right.
the.
Right. Right. But this one, you can see that we're changing the topology here as well, right? Introducing more holes. But I agree with you that, if your data has 0 holes, it's not gonna capture after training. You won't capture things with more holes. Yeah. So
Okay.
really, I think the idea is that now we can train with different topologies, which is not possible, at least in the reduced order modeling context. That's not even possible before.
Right.
Yeah. So
Sure.
just the fact that you
Totally.
can train with different topologies is sort of a first step.
Yeah. Okay.
It's not going to, yeah.
Yeah. Thank you. Yeah.
All right.
Thanks, Peter. Yeah, I guess we're a little over time. G, do you want to wrap things up?
Yeah, I usually make an announcement to sponsor speakers, but as we have a full list of talks coming, thank you everyone for joining. Thank you, Peter, so much for the talk. And I will follow up with you to share the recording with folks outside of research, if that's okay with you. And for those who couldn't make the talk, I'm sure they'll be eager to see the upload of today's talk. So thank you everyone for your time. Peter, thank you so much for making time and for the awesome presentation. All right. Bye, everyone.